before doing this, let me just some reminders from yesterday. First of all, I want to make a correction of a small mistake I made. I will be very brief about it. I told most of you. Considering KK, the composition for SLN, using that KK decomposition, using the KK decomposition we put for DLN, we got D being K, A, K prime, where that A is 1 and that K must have been equal to K prime, and it was, can you see this? It was in plus minus 1. In case both guys have a minus 1 determinant, then use K and take this matrix here, A, same matrix here, K prime, and since A is a diagonal matrix, these guys commute and they invert each other, so this is fine, and it fixes that determinant, and that determinant to be plus 1. Okay, so this is just one small correction. Another thing before starting today's material is an exercise that I want to give, and I want to give some hints, so I want to emphasize this in class. And this is, given what we've done yesterday, this should be rather easy. Prove how move curve. So I'm going to state this and to explain how one proves it using what we've done. Well, for SLN. Same proof will work for any semi-simple group once you know some structure theory, or use what we said last time. If G is mapped to the unitary operator on some V, so here V Hilbert, and this is a unitary representation, and if there are no invariants, no G fixed points, then matrix coefficients, I will explain this if you don't know, go to 0. So those just came. Today's title is metaheterodicity. What I'm doing now is giving an exercise, an important exercise about the material of last time.
Do you mean by going to 0?
Sorry?
What do you mean by this last thing?
Yeah, I'm about to explain. So, and this means for every V prime inside V, if you look at this matrix coefficient and you take G to infinity, let's say a sequence going to infinity in G, or just take G to leave every compact set in G, and this will be less than given epsilon. I mean, okay, we all know what converging to infinity is. But again, if you like, you should take a sequence. Or equivalently, this is an equivalent formulation. The vector GV, V in V, think of v prime to be an arbitrary guy, then gv goes to 0 when g goes to infinity in the weak sense.
G goes to infinity.
So infinity. So I will give some hints how to go and prove it and leave the details for you. To you. Since I will not use it in the SQL. Here. We know that stabilizers. So if we omit 0, the only fixed point, and think of V as a metric space with the Hilbert norm, we know that stabilizers are compact. So just subgroups of G. And actually we know that the orbits are close with respect to the norm topology, but somehow this is not enough. What I want to convince somehow behind the scene here is that the orbits are actually close with respect to the weak topology as well, outside of 0. So the only closure point of an orbit is 0 itself. The weak closure of an orbit is just the point 0. This is what we are actually proving. Show that if I'm having a sequence, g and x and y are vectors here, goes to y, and this is weakly, then stub y is not compact. This will be the strategy. This will force y to be 0. Actually, it's like correction, but I will do it for some y prime. And this y prime will be k inverse y. Well, it will be something in the orbit of y. But of course, there are 0. Y prime is 0 if and only if y is 0. For some k in g. Actually, k in k. And maybe just this k will be the limit of kn, and you will show that u plus is in the stub for some decomposition kn, an, kn prime, and this is u that is associated with the an thing. Okay, so I leave you to fill details. It is rather easy. You just have to be slightly careful about where you use weak convergence and where you use norm convergence. So this is the only thing, and again, I'm leaving it to you. Oh, maybe just one more remark. Whenever you have a sequence Gn, up to subsequence, there is some weak convergence using compactness, weak compactness of the closed uniform. Okay, so you should use this as well. And what you want to show is that you are converging to 0. Okay, that's what I wanted to say about Haomu. This is the name of the actor. And I want to start now with this subject of multiplicity. So before making a definition of this concept, let me restate something we already proved yesterday for G, which is SL and R, and actually for various groups of similar kind. And for H in G non-compact, every invariant continuous semi-metric on G mod H. Continuous means that the map D from G mod H times G mod H to the rings is continuous with respect to the natural topology on G mod H. And the natural topology on G mod H is the quotient topology. That topology that makes the map G to G mod H on. So for every blah 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 blah, every is trivial. So what we've seen yesterday is that if G acts on a metric space with no fixed points, then the action is proper. The stabilizer will be compact. Here I'm assuming having a non-compact stabilizer. This is not a metric space. A priori it's a semi-metric space, but whenever you have a semi-metric on a given space, there is an obvious equivalence relation for points being of distance 0 between one another. This equivalence relation is respected by the G action, so I can mod it out. I'm not about to write down what I'm saying now. I'm about to explain. We have a semi-metric on G mod H. There is an obvious G invariant equivalence relation of pair of points being in distance 0 from each other. And if you mod it out, you get some quotient space on which the semi-metric descends to an actual metric. But this quotient space will be a transitive G space as well. So it will be of the form G mod, I don't know, some H tilde. So this will give a metric, an actual metric, on some quotient space. G mod H tilde. H tilde will be a closed, non-compact subgroup in G. So the previous theorem compactness of stabilizer, unless fixed point, will imply that H tilde is G. Is that argument clear? Excellent. So this is a nice theorem, but actually, if you think about it, you get much more. Corollary. My mission now is to remove this continuity assumption that is there and replace it by immeasurability assumption. Maybe I should say it is not correct that every measurable metric on G mod H is trivial. For example, the discrete metric is measurable. It doesn't give, the measurable structure that gives is not the same as the measurable structure of G mod H, but as a function, d from G mod H to times G mod H to R, it is a measurable function. I mean, the diagonal is measurable in G mod H times G mod H. And it sends this one to 0 and everything else to 1. So there are measurable functions, measurable metrics on G mod H. You can ignore that. So what I'm writing now is that same setting, same T and H. Every measurable I mean Borel. separable. So I want the metric to give a separable metric, separable topology. Separable means that you have a dense set of cardinality of Aleph 0. A dense countable subset. Separable metric. On G mod A. Is trivial. Invariant. Every. Thank you. Okay, let me give you proof of that. Let D be such a metric with all these adjectives, such a metric, and let me discuss metrics and not say metrics, as we understand how to reduce one to another. Metric on G mod H we will show that D is actually continuous. So actually we will show that the map G mod H, let me call it T, this is the standard topology. To G mod HD, the metric topology, is continuous. Actually, this is one more reduction. We show that the map G to G mod HD is continuous. And of course, we have the canonical map here. And the fact that this map is open, or if you wish, the universal property of the Cossack space, will give us a continuous map of this form. Okay, so this is what I'm working on now. I want to show that once you have a metric on a Cossack space, which is measurable and separable and invariant, then it is already a continuous metric. Actually, in exercise using Bell category argument, which you're maybe familiar with, shows that these two are actually the same. This must be a homeomorphism, eventually, after the fact. Okay. And here is how it goes. Or maybe, again, let me explain what I need to do. Let me do the reduction. Need to show that the play image of the ball PEH, epsilon here is arbitrary, or peak epsilon greater than 0. We need to show that for every epsilon, the play image of such a ball contains an open identity neighborhood. In G. I care about things at the identity because things are invariant anyway. I can translate this ball around. Okay? So this will give me continuity if you have continuity of the identity, I will have continuity at every point. This is not an issue, so I'm working at the identity. Again, this is for every epsilon. I didn't write the quantifiers. I'm being a bit sketchy. The thing is that balls look alike everywhere. So find or cover G mod H with a countable family of half epsilon balls. Here I'm using the superbit. And the thing is, this countable family that covers as a full measure. And it is countable, so one of these balls as a positive measure. One, as any of these of the pre-images. Now think in G of the pre-images of these balls will have a positive measure. How measure? Now I'm talking about G. The pre-images of this countable family cover G. Consider the Haar measure of G. I'm not working with the Haar measure on this cosset space. I don't know if there is an invariant measure here. I'm working in G. I have a countable family that covers, and one of these guys will have positive measure, but they are all translate of each other because the metric is invariant. So if one has, by invariance of the measure, if one has a positive measure, then all have a positive measure, and in particular, and also, pi inverse of the ball at the identity, epsilon half mode. Let me call this like A. Will positive measure. Okay. Now, an easy exercise for you. Observe that A equals A inverse. If X is at epsilon distance from the identity, then X inverse is at epsilon distance from the identity. Right? And also, this is why I took epsilon 0 here. A times A, taking multiple of all pairs in A, in G, is contained in what? In the pre-image. Thanks. Of the epsilon bond. This is triangular inequality. And the invariance of the metric. But AA inverse, which is A square, always means for A with positive measure. I hope you know this fact, that if you take a set of positive measure in a group, and you look at AA inverse, it does contain an open identity in a group.
We could know it for circle.
Sorry?
We could know it for circle, for example, not for arbitrary group.
So, okay, so I'll put this, I'll put this as one of the exercises. I'm going to use this fact. it's of the same order of magnitude as convolution of L1 function is continuous, or something like that. So it's a classical fact in topological groups. I don't want to look at it now. Oh, probably, yeah. Always contains an identity level. And we are done. This is the identity neighborhood in the pre-image of ball. Okay. A part of this fact which I did not explain in full. Any questions? So now take a look at this corollary, and I want to phrase it as an ergodic theorem of a certain time. So let me make a definition. Let X, because G mod H, be a Lebesgue space. And actually, I'm kind of doing things in a reverse order. I'm about to discuss what do I mean by this precisely later on. But for now, this is a standard a Polish space, a separable complete metric space with a measured class on it. And assume G act on X by automorphism of Lebesgue space, measurably reserving the measured class. As we have for G mod H and the Haar measured class. We say that the action is metrically ergodic, or sometimes isometrically ergodic, abbreviation sometimes to ME, if for every separable metric space UD, or making this, okay, on which G acts isometrically by this I mean if G is a topological group, so also the action is continuous with respect to G itself, right? The map G times U to U should be continuous, and the natural map from G to the symmetry group of U should be actually be into the isometry. I'm not writing all the adjectives which I hope are understood. For every separable metric space and isometric acting by G, and for every adjectives measurable map of G equivariant I'm analyzing the form. G equivariant map X to U is essentially constant. So this is a new definition. It might take a while to get used to. So this is what we discussed about. constant, by the way, will be a G invariant point. It must be, of course, since the map is invariant.
Could you remind us what it means to be Lebesgue?
So actually, I will spend more time in the near future about it. I said it orally. This is a nice metric space, a separable complete metric space with a measure class on it.
And G equivalent map, what is it?
So just respect the G. So it's
Okay.
Could you give a motivation for this definition?
yes, I will. I gave this definition because this is another fancy way to state that property. But it's a useful way from the point of view of ergodic theory. So somehow, ergodic theory is the study of maps between measurable spaces into or measured spaces, space with measure class, to Borel spaces. And ergodicity is saying no invariant maps to the reals. And this is saying no non-trivial maps into metric spaces. So maybe let me give the following example.
So could you relate metric ergodic to ergodic?
Yes. Remark. The special case. U being 2 points. And with the trivial action, well, I guess with the discrete metric. And trivial action gives metric ergodicity implies ergodicity of the action of G on X. So if G act on X metrically ergodic, it satisfies all these nice things. If we just consider a space with 2 points, so this should somehow emphasize how much more this is than just ergodicity. Just a space of 2 points, if you have a map, equivalent map to the trivial action on 2 points, this means a constant map. Sorry, this means an invariant subset, the parameter of 1, say, in X. And to say that this must be essentially constant, this means that this invariant subset is either full or empty, or none.
So key thing in this remark is trivial action, not 2 points.
Yeah, here only you have a trivial action. So somehow in classical ergodic theory, we study maps, invariant maps, from measured spaces into Borel spaces with no action on this. But it became clear that sometimes you want to study maps from spaces with action to spaces with action, and to say, hey, you don't have map with this specific action. Okay? I will relate this definition to more, if some of you are familiar with classical ergodic theory, I will relate it to this in a minute. I just want to make one more useful remark. In the definition, one can restrict himself or herself to bounded metric spaces. So I may assume that the diameter of U is bounded by 1, just by changing D arbitrarily, I mean, replacing D with the minimum of D and 1. It's another metric which gives the same structure. And the isometry group is just the same. So it doesn't really matter. And sometimes it comes about handy, this little observation, so I state it right away. So, any more questions? I will give some examples, but any more questions about the definition? Is everything understood? So let me now just state this corollary again using this term. So, corollary again.
So, why do you assume separable metric, not locally compact or anything else?
So, locally compact is just not strong enough to my wishes. And separability, actually, whenever you have, okay, I don't want to discuss those fundamental issues, but when you have a backspace and you map it into a metric space, the support of the image is always separable. So I could omit this phrase, but it's easier to handle when I do put it. And you see it essential importance here. We use the probability, and you saw this in the proof. I could have not written this probability, but then I would have to assume another sort of measurability on the metric. Not just the metric, D from G mod H times G mod H to R is measurable, but actually that the measurable structure that it gives on G mod H is the same measurable structure as the original one. This is a stronger sort of measurability, and if you assume this, this will give you probability for free. I don't want to actually put myself in this corner. And now I'm estimating the corollary. If G is SLNR, H in G non-compact, then the space X equals G mod H, or the action G on G mod H, is metrically algorithmic. Whenever you map this space into U, well, you can pull back the metric from U to G mod H. Whenever you map it measurably, you will get a measurable, separable, same metric on G mod H, but it must be trivial. So it means that all points have images with distance 0 from each other. It means that the image is constant. Constant G point, G fixed point. And somehow, it is useful for me to have this term over there, this corollary, in that form. I will explain why, or it will be clear why in the near future. Of course, this is just a synonym. But now, before ending this hour, I want to give another example. Another example, or another class of examples. If X is doubly algorithmic, so I'm in the setting discussed before. X is a Lebesgue space, and X is doubly algorithmic. This means that G acts not only on X, but on X squared with the product measure is algorithmic. Then, actually, X has the very strong property of being metrically algorithmic. We give proof of that. Consider the map from X times X. Assuming we have some map to some U. Consider the map from X times X to U times U. Now, this should be a G invariant map, because the metric is invariant. Is G invariant? Hence constant. It means, well, if this constant would be 0, this means that every 2 points in X goes to the same point, and the map is constant. The map X to So let us discuss what is this constant is, I don't know, something else, 1 or epsilon or whatever, 1 million. It means that X sits as a separated set inside U, the image. But U is separable. And X is not. Well, I have to argue about this. But since, let me start by saying, since X has no countable factor, the image in U is either a fixed point or some uncountable discrete set. I should explain this. Don't look at me like that.
I'm not arguing that, but okay, it's constant.
Unhappy in general.
It's constant up to set of measure 0, which lies somehow in this product, and then
Yes, it's essentially constant. It's the same.
it's essentially separated set. No, I just cringed. So-
Okay, no, okay. It's, you have the right to get a little shiver here and beware about the details. I'm not giving.
You know, I'm trying to digest, you know.
Okay, so let me finish though. We deserve the break. Since there's no countable factor, so the image of X in U, I claim, and I will explain this in 1 minute, is not countable by separability of U. X times X, I mean, fx is 0, and the image of X is essentially constant in U. And now I need to explain why if G acts on X squared godically, then it does not have a countable factor. And let me do it orally and rush to a break. This is really very easy. Well, if we had a factor y of x, the action of G on y, a factor means just such guy that you have an equivalent map from x to y. This is what I mean by a factor. Then the action of G on x squared would be, if this is a godic, then this is a godic as well, right? If I would have an invariant function here, I could put it back here and get an invariant function here. No problem. But if this was countable, the measure would be atomic, right? It will charge positively at atoms, and then I will have in y squared at least 2 invariant sets. Unless y is a point, I will have the diagonal and the rest. These are nice things to keep in mind, that measurability of the diagonal in x squared, sorry, positivity of the measure of the diagonal in x squared is equivalent to having atoms in X. This is a little thing that is very useful to have in mind. And since we can't have it, we can't have 2 orbits here, it can't be